All right, what is up, people? Hopefully all are doing well, and yeah, surviving quarantine. So, chapter 14, lesson 4, we're talking about gases, mixtures, and movements. So we're still talking about gases. Okay, so mixture of gas. In a mixture of gas, each individual gas exerts its own pressure, called its partial pressure. So the partial pressure is the contribution made to total pressure by one gas in a mixture, and the total pressure of a mixture of gas is going to be the sum of all these partial pressures of all gases in the mixture. This is expressed by Dalton's law. So we're going to get into Dalton's law here. Let's look at this picture. Basically, in this picture, we have volume and temperature are constant. So if we have the same volume throughout here, right, we've got our gas 1, our gas 2, and then this is a mixture of our two gases. We can see the pressure of gas 1 is at 1 atmosphere, the pressure of gas 2 is at 2 atmospheres, and then when we mix those two gases together, our pressure is going to be at 3 atmospheres. So in each of these, we have the same volume, we have the same temperature, and we're just mixing them together. So our total pressure is equal to the pressure of gas 1 plus the pressure of gas 2. So again, this is expressed by Dalton's law. What Dalton's law says is that at a constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the component gases. So we have this mathematical equation that sums this up that we can use in our different problems. So the total pressure within a mixture is equal to the pressure of gas 1 or exerted by gas 1 plus the pressure exerted by gas 2, so on and so forth. So again, here's another example. The total pressure in a gas mixture is the sum of the partial pressures of each individual gas. So if our total pressure is here, we see 4 atmospheres of pressure. This is both gas A and B. Well, if we were to take just gas A in that same container, gas A would only have a pressure of 1 atmosphere. And if we were only to take just gas B in that same volume of container at the same temperature, gas B would have a pressure of just 3 atmospheres. So a mixture of those two, we take 1 plus 3, and that gives us our 4 atmospheres of pressure when we have those two in the same container, once we combine them together. Okay, so here's an example problem using Dalton's law. A gas mixture containing oxygen, nitrogen, and carbon dioxide has a total pressure of 32.9 kilopascals. If the pressure of oxygen is equal to 6.6 kilopascals and the pressure of nitrogen is equal to 23 kilopascals, what is the pressure of carbon dioxide? So again, notice for oxygen naturally is a diatomic molecule, so we have O2. Same with nitrogen, naturally a diatomic molecule in N2. So you guys go ahead and pause the video here, work that out on your own. It should be fairly simple, and then I will end up working out for you. Okay, so here all I'm going to do is, I know that my pressure total is equal to my P1 plus P2 plus P3. So all I do is I take, what I want to figure out is the pressure of carbon dioxide. So my pressure total is going to equal my pressure of O2 plus my pressure of N2 plus my pressure of CO2. So to figure out CO2, what I do is I take my, total pressure minus PO2 minus pressure of N2. So 32.9 minus 6.6 minus 23. And that's going to give us our answer, which is 3.3 kilopascals. And that is our partial pressure of CO2. Okay. Again, make sure that we are using the right units. We're labeling our answer with these units. So I'm labeling my answer with kilopascals. You should get in the habit of labeling these as well, just to keep track of what units that we're working in. Okay, so the next thing that we're talking about is the movement of gases. So there are two types of movement that our gases are going to experience. We have diffusion and we have effusion. So for diffusion, what we're talking about is that we have molecules of gas in an area of really high concentration. So this is like if we end up spraying perfume in a room. What's going to happen is those molecules of, well, in that case, perfume is a liquid, but if we're talking about a particular gas, if we have a very high concentration of it, what it's going to do is it's going to move from that area of high concentration and it's going to slowly spread out to areas of low concentration until the concentration is uniform throughout that particular area. So diffusion, we're just going from high concentration to low concentration until we have the same concentration all throughout. Effusion, on the other hand, is the movement of a gas as it escapes from a tiny hole in its container. So that will be effusion. So if we think about balloons, if I have a balloon and it has, that's my balloon there, it has helium inside of that balloon, what's going to end up happening is that helium is slowly but surely going to leak out of the balloon. So that movement of the gas outside of the balloon is called effusion. When we're examining this movement, what we notice is that gases that have a lower molecular mass, so their particles have lower mass, they're smaller, this is directly correlated to the rate at which they diffuse or effuse. So they're going to diffuse and effuse, they're going to move faster. So they have faster rates of diffusion and effusion if they have lower mass. So the lower the mass, the faster the rate. So this principle is expressed by Graham's law. Graham spoke simply of effusion, but this also applies to diffusion as well. So the rate of effusion of a gas is inversely proportional to the square root of its molecular mass. So this is going to be the equation that we use when working with these different problems right here. We have the rate of one gas divided by the rate of the other. So in this case, what we're doing here in this part, we're looking at the relative rates of diffusion or effusion. So we're seeing like how much quicker are we moving with one gas compared to the other. So in this equation, we have the rate of one gas divided by the rate of the other. So the ratio between the two is equal to the square root of the molar mass of the second gas divided by the molar mass of the first gas. Okay, so make sure that we focus on, this is talking about molar mass of A, and over here we have rate A is on top, molar mass of A is on bottom. Rate B is on bottom, molar mass of B is on top. Okay, so our example problems here, I have how much faster does helium effuse than nitrogen at the same temperature? So all I'm going to do is I'm going to use Graham's law. So I know that my mass of helium is 2, whereas my mass of N2 equals 28. Again, because nitrogen naturally is a diatomic molecule, I have to take the mass of N2. So my rate of helium is going to be, so rate of helium over my rate of N2, this equals the square root of 28 divided by 2. So when I solve that out, my 28 divided by 2, I end up getting the square root of 14, which if I take the square root of 14, I end up getting something around 3.74. So 3.74. So what I know then is that my helium effuses 3.74 times faster than nitrogen. All right. So, cool. So helium diffuses 3.74 or effuses 3.74 times faster. So I'm going to erase that so that we can do the next problem. Okay, so the next problem, calculate the ratio of velocity of hydrogen molecules to the velocity of carbon dioxide molecules at the same temperature. So you guys go ahead and pause your video. You guys go ahead and try and figure this out, and then you can play the video again to see me work out the solution. Okay, so the ratio of hydrogen molecules to the velocity of carbon dioxide molecules. So my hydrogen, again, is going to be diatomic. So it's going to have a mass of 2. My carbon dioxide has a mass of 44. So the ratio of velocity of hydrogen molecules to the velocity of carbon dioxide, I'm going to set this up the exact same way. So that ratio is going to be equal to, since I want hydrogen to carbon dioxide, hydrogen is gas number 1. So I'm going to put that on the bottom here. And I'm going to put 44 on the top. So my ratio equals the square root of 22, which if I calculate that out, square root of 22 equals 4.69. So my ratio of velocities of hydrogen to carbon dioxide is 4.69. So once you guys have finished watching this video, you have a worksheet that is attached to your e-learning. Go ahead and work out the problems on the worksheet on your e-learning.